the goal then, after these 3 lectures, will be to understand the origin and evolution of large-scale structure. And as I said, one can divide the problem into 2 parts. The first, when fluctuations are very small, that's linear theory. And Chung-Pe Mai yesterday talked about that. So I'm going to go very fast through this because she's already covered a lot of this material, but I want to cover it in a slightly different way and introduce some notation. And then I'm going to spend most of my time talking about the nonlinear phase when the perturbations are now large. And then I'll finish off saying something about how we can use galaxy surveys to test our cosmological models. Now, these topics, of course, are very intimately connected to 3 of what I would call some of the most outstanding problems in 21st century science, not just physics. That is the identity of the dark matter, the nature of the dark energy, and the origin of cosmic structure. I think these 3 are some of the key problems, unsolved problems, that we hope to be able to perhaps solve this century. So, a lot of what I'm going to say, particularly the first part, there's some notes that you'll see some equations in a minute that come from these notes. This is going to be on the web, so you don't need to worry about copying these. There's some lecture notes that develop linear theory in a fairly succinct way, and I copied some of those notes in here. And then there are a number of books that set out the basic ideas of what I'm going to be talking about, although I hope to go beyond what you can read in books. So let me then begin by getting us in the right mood and talking about large-scale structure by showing you a picture of the real large-scale structure in the universe. There are 2 surveys that have been done in the last decade or so, which have really completely transformed our view of the structure of the universe. One of them is the 2DF Galaxy Redshift survey, shown here, and the other one is, all right. Okay, and the other one is the Sloan Digital Sky survey, which one of the phases of which has just recently finished, and they have collected over 500,000 galaxy redshifts. So let me show you, I'm sure most of you will have seen pictures like this, but maybe not everyone. So let me show you a movie that illustrates the large-scale structure as represented in the 2-degree field galaxy redshift survey. So where this is a little bit of a promotional movie, so the first part is mostly for kids. The science comes at the end, but we're flying through the 2DF Galaxy Redshift survey, which, as I say, is a survey of about 250,000 galaxies, and in 2 hemispheres, the north and south, and we're going to see it in a minute. These are the positions of the actual galaxies. The images are not the real galaxies in the survey, but they're galaxies that share the same properties. And here we finally see, obviously the observer is situated here. The survey has 2 parts, a northern and a southern galactic pole regions. And you see here then in all its beauty the large-scale structure of the universe. You see the fact that galaxies, of course, not distributed at random. They're clumped on all scales, from small groups and clusters of galaxies to these very large superclusters, some of which extend over a large fraction of the sky. They have typical dimensions of 100 megaparsecs or so. So that is what we're trying to understand. And as I'm sure all of you know, the very exciting development in cosmology of the last 25 years or so is the realization that all this structure comes from quantum fluctuations in the early universe. Now, Chung-Pe told you what the universe is made of and showed you this famous picture. I've collected some numbers here because, in fact, in addition to dark matter, dark energy, and baryons, the universe does contain other things. In particular, it contains, of course, radiation. The radiation makes a very small contribution to the total mass energy budget of the universe. Here, all these are given in terms of omega, which defined as the density in units of the critical density. And the density here includes non-relativistic mass, relativistic component, and a vacuum energy. So radiation contributes a very small amount to omega. but neutrinos can actually contribute more than radiation depending on what the mass of the neutrino is. Here, for example, so if the neutrino has a mass of a few tenths of electron volts, then they would contribute more today to the energy density than the radiation itself. The baryons, of which, as was mentioned in the discussion yesterday, only a very small fraction, only a few % of the baryons that we know must be there are actually in the form of stars. It's less than 5% or so of the baryonic content of the universe is actually in the form of stars. And then there's the dark matter and the dark energy, all of which amazingly add up to about 1. So we know, of course, that since most of the mass in the universe is not in baryons, it must be something else. And really, unless one appeals to radical modifications of gravity within the context of general relativity, then it's clear that the dark matter must be some kind of weakly interacting massive particle. And that, in fact, is the viewpoint that I'm going to take in these lectures. So as I said, structure goes back to inflation. I don't know if Eric is going to talk about inflation. No? Nobody's going to talk about inflation? All right. OK, I guess inflation is old hat. It's 25 years old. So I'll just remind you that inflation predicts a flat geometry for the universe, which, of course, is what we appear to have. And also small fluctuations imprinted in the universe very early on. And one simple way to think about how these fluctuations come about is sketched here in this diagram, which I think comes from a book from the person who first talked about inflation, Alan Good, or one of the first. I think I got this from his book. And what you see here is the fact that because of quantum fluctuations, when the universe, so not every part of the universe emerges out of inflation at the same time because of these quantum fluctuations. Different parts of the universe finish inflating at different epochs, and then that seeds the universe with these small fluctuations in the energy density, which are adiabatic, meaning that everything, matter, radiation, everything is compressed in the same way. And also, because these are quantum processes, then the phases are uncorrelated, and so the distribution of amplitudes of these fluctuations is Gaussian. Then as the universe inflates, these fluctuations are blown up to macroscopic scales. They extend beyond the horizon, and then eventually they come back inside the horizon. So in following the linear theory of fluctuations, then, it's important to distinguish between fluctuations that are outside the horizon, as illustrated here, from fluctuations that are inside the horizon, because it's only when they come inside the horizon that physics can operate and affect the evolution of the fluctuation. When the fluctuation is of superhorizon scale, it's actually quite easy to show that the fluctuation just grows. And it depends, the growth rate depends on whether the universe is dominated by matter or radiation. If it's dominated by radiation, the fluctuation amplitude, delta is just the dimensionless fluctuation amplitude. I think the next slide gives you the mathematical definition of it, but it's just the dimensionless fluctuation in the energy density. That grows as a squared if the universe is dominated by radiation, and just as a if the universe is dominated by matter, where a is the expansion factor. Eventually, the fluctuations come inside the horizon, or the horizon expands to encompass the fluctuation, and then interesting things can happen to them. So I'm going to go very quickly through this. It's quite elementary, but it's mostly to establish the notation. The linear phase of evolution, namely when this delta is much less than 1, can be solved mathematically in quite a simple way. And that describes the evolution of fluctuations essentially in the early universe. And that theory is well established. And for those of you who haven't seen it, I'll just highlight some of the main results. So first of all, we're doing linear theory. So we expand the density, pressure, and velocity fields in terms of a mean quantity and a perturbation and a perturbative term. And the definition of delta that I used earlier is here. It's just rho minus rho mean over rho mean. That's what I mean by delta. And then the equation, so we treat the entire content of the universe as a fluid and as an ideal fluid. And in the case where the fluid is non-relativistic, the equations one needs to solve are these three equations. the continuity equation, the Euler equation, and the Poisson equation, because everything is coupled through gravity. So these are the equations one needs to solve, and they're analogs of this in the relativistic case. And so what you do is just you linearize these equations, and you do a little bit of algebra, and then you derive the basic growth equation for evolutions in the early universe, which is shown here. And this gives the second derivative of this dimensionless perturbation. Here's the Laplacian of the perturbation in pressure and of the peculiar gravitational potential. Now, this term is very important, and this is just a typical equation for fluctuations. It's quite general, apart from this term, which is the only one that includes cosmology. That's the whole constant there, and this is sort of friction term, thanks to which we're here. If it wasn't for this term, life would have not evolved, because in the absence of this term, it's easy to see that fluctuations just grow exponentially, and there would be no time for stars, galaxies, and people to evolve. So we should be very thankful for this friction term in this equation. Now, so these equations can be solved in special cases. In particular, if you're worried about dust, if you want to follow the evolution of dust, basically cold matter with zero pressure, then you can solve the equation exactly in two limiting cases. One is when the universe is dominated by matter, omega matter equals 1, where you find the well-known solution where this dimensionless perturbation grows like t to the 2/3. All these solutions have a growing and decaying mode. This decaying mode decays away, and you see it actually quite nicely in simulations. You see it decay away, and then this term is a growth term, and in this particular case, the delta just grows in proportional to t to the 2/3. The other case that can be solved exactly is a lambda-dominated universe with omega lambda equals 1, no matter. And in this case, here's the decaying term, and there's no growth term. In the case of a lambda-dominated universe, the universe just expands so fast that fluctuations no longer grow. And the structure then freezes out. There's no more opportunity to grow. Of course, we live in a universe that's in between these two. So here is a comparison of the growth rates of fluctuations. And here's a function of redshift. That's the growth rate. And all normalized to 1. And here are two cases of interest. So you see here, as we just saw in the previous transparency, that if omega matter was 1, then fluctuations would grow much faster than in a universe with a dark energy or a cosmological constant in this case. This is still not completely lambda dominated. I think these numbers are the other way around. Sorry, this should be lambda, this should be matter. It's not completely lambda dominated, so there's still some growth. If once the universe goes lambda dominated, then the growth essentially stops. And these are other cases that I might come back to in a couple of lectures of universes with different forms of dark energy. Now, so one key concept when considering linear theory is the concept of the Jeans mass. And that applies to every component of the universe, but it's particularly relevant for baryons. That is, for a component that has pressure. And in this case, if you take the pressure perturbation to be proportional to the density perturbation and express it as a plane wave, then you go through the equations, and you find this very interesting equation, which is interesting because here on the right-hand side, same equation we saw before, there are two terms competing with each other. Obviously, because there's a g there, this is a gravitational term, this is a pressure force, and as you can see here, there's a balance between gravity trying to cause the perturbation to collapse, and pressure trying to resist the collapse. When these two terms are equal, then that happens for a particular value of the wavelength, which is called the Jeans wavelength, associated with which there is a Jeans mass. And so what this equation tells us is that if you have a perturbation that has a mass bigger than the Jeans mass, then gravity wins and the perturbation collapses. If you have perturbation with a mass less than the Jeans mass, then pressure is more important. And what happens to these ones is that they oscillate as acoustic waves when the mass is less than the Jeans mass, keeping a constant amplitude. So there's these two regimes. Mass bigger than the Jeans mass collapses, mass smaller than the Jeans mass oscillates at constant amplitude. And the interesting thing is that you can see here the Jeans mass scales like the third power of the sound speed. And before, when the universe is dominated by radiation, all the pressure, as George said yesterday, is due to radiation. And the sound speed for radiation is c over square root of 3. So the Jeans mass during this epoch is very, very large. In fact, it's larger than most astronomically interesting objects. The Jeans mass is about 10 to more than the galaxy cluster mass. And so all these perturbations, all perturbations of scales that are of astronomical interest are below the Jeans mass, and so oscillate as acoustic waves. And then when the universe becomes matter-dominated near recombination, then the Jeans mass plummets because the pressure is now gas pressure, and the Jeans mass becomes very small. So all these fluctuations, which were happily oscillating before recombination, can finally collapse. That's just because the sound speed plummets at recombination. Now, there was some discussion yesterday about when we consider, now let's go back to dark matter for a minute, and to cold dark matter. And cold dark matter experiences a process known as the Mesaros effect, which happens during the time when the universe is dominated by radiation. So what happens here is that if you imagine a perturbation that's bigger than the horizon, as we said earlier, it's growing in proportion, say during the radiation era, in proportional to a squared. And when this perturbation comes inside the horizon, then the radiation very quickly becomes uniform, and the perturbation in the dark matter suddenly realizes that it's now been left alone. The radiation smoothed out, and so that stifles the growth of this perturbation in the cold dark matter. That's called the Mesaros effect. Another way to think about it is just the universe expanding much too fast. In the radiation era, the matter cannot keep up with it, and so fluctuations in the dark matter, in the cold dark matter, cease to grow during the radiation era. And it's very easy to show how this works. Here's the perturbation equation for the appropriate case of cold dark matter, and you just need to do some change of variables. You can go through all the equations in the notes in the quiet of the beach if you feel like it. It's actually very easy to show that in this case, then there's only between the time when the perturbation comes in the horizon and I think, let me see, and recombination, and when it goes non-relative, well, and between then and the moment when matter and radiation have equal energy density, these fluctuations only grow by a factor of 5/2. So it's very easy to show. And then the last effect that I want to mention, Chung-Pei already talked about it yesterday, is freestreaming. And that happens when when the perturbation enters the horizon, and if the matter is still relativistic, say if the dark matter is light particles, still relativistic, then relativistic perturbations tend to dissipate because the particles are moving so fast in 3 dimensions, they just free stream out of fluctuations, and then those fluctuations are completely damped away. And the characteristic wavelength for this damping for thermal particles scales like the inverse power of the mass. Okay, so let me then summarize what I've said in pictures. Please stop me if either I'm going too fast or, as I fear, too slowly. If this is all too elementary, just let me know and I can get on to other things. But maybe it's too late now because I finished with this. But if I am going too slowly, please let me know. If I'm going too fast, likewise. So. Any comments? Oh, somebody needs a phone call, isn't it? All right, okay, so let me summarize here where we are. So here is the evolution of a density perturbation in cold dark matter. And there's these 2 important phases that I mentioned. This is when the perturbation comes inside the horizon, so it's been growing while it's outside the horizon. And then between horizon entry and matter radiation equality, the Mesaros effect stifles the growth of the fluctuation. Otherwise, it would have continued growing like this, but it doesn't because of this effect that I just mentioned. And then after the epoch of matter radiation equality, it can take off again. And contrast that with the evolution of a baryon perturbation. Again, outside the horizon, it grows, but this is a sub-Jeans mass perturbation, so it oscillates as acoustic waves, keeping constant amplitude. And that's, of course, the origin of those Doppler, so-called, incorrectly called Doppler peaks in the microwave background radiation. They come very closely associated with these oscillations in the baryons, which are coupled to radiation before recombination. So these coherent oscillations of the photon baryon fluid is what gives rise to the features, the Doppler peaks in the microwave background radiation spectrum, and also to something that I will talk about later, the baryon acoustic oscillations that we see in the galaxy distribution. They all come back to this picture. Once the universe recombines, here T2 is the epoch of recombination, then the gene's mass plummets, perturbations grow, and the baryons then quickly fall in, catch up, and fall into the potential wells produced by the dark matter, which has been growing, has a head start compared to the baryons. So now, I think Chung Pei also talked about this, so just to establish some notation, so far, we've been following the evolution of one perturbation. Of course, there are perturbations of all wavelengths around, and so we're interested in the power spectrum of perturbations. So you expand these dimensions of this perturbation field in a Fourier integral. And then what I mean by the power spectrum is P of k is just the square of the modulus of the Fourier coefficients of the perturbed density field. So that's the power spectrum. And that then tells us the amplitude, the total power in a particular wavelength of wave vector k. So k here is wave vector, 2 pi over lambda. Now, if you are looking at a region of space and you have waves of many wavelengths or frequencies contributing to the density perturbation there, and you want to know what is the total amplitude of the mass perturbation in some region, then you have to do an integral over the power spectrum multiplied by a window function. And this quantity is the mean squared value of the fractional perturbation in mass, so delta m over m squared. It's just an integral over the power spectrum, and that's what I call sigma squared. So these two quantities are going to appear quite regularly in the next few minutes. So P of k then is just the power spectral density, and sigma square is the variance in the mass fluctuation integrating over all k's. Okay, so then, although for realistic cases, the power spectrum has some complicated form because of all these processes that I described, it's often convenient to approximate the power spectrum as a power law, which may be valid over a limited range of k. And then if you write the power spectrum as k to the n, then you can then do that integral of sigma squared. And it turns out then that sigma squared is proportional to the mass, to the minus alpha, where alpha is given by this, and n is the exponent of delta k, of P of k. Delta k squared is k to the n, and then alpha, which gives the variance in the mass fluctuation, the dependence with mass, is related to n like this. And I'm going to show in a minute that inflation predicts that n should be equal to 1, the so-called Harrison-Seldovich spectrum. In fact, I'm going to do that next. So, so as I said very quickly a few minutes ago, in the standard model of cosmology, fluctuations are produced, the perturbations in the density field are due to quantum fluctuations during inflation. And these fluctuations are adiabatic and have a Gaussian distribution of amplitudes. Now, as I said earlier, as the universe inflates, the perturbation stretches beyond the horizon. But then when inflation stops, the horizon now grows more slowly than it used to. And eventually, the fluctuations re-enter the horizon. Now, inflation is an exponential process. There's no scale associated with it. And so this process is self-similar. And what that translates to in practice is that when a fluctuation re-enters the horizon, it does it with a fixed amplitude regardless of its wavelength. George, again, alluded to this yesterday. So by self-similarity, fluctuations all after inflation all have the same amplitude when they come inside the horizon, independently of wavelength or independently of the path of the perturbation. So that scaling variance then leads directly to the fact that inflation predicts that n should be actually not exactly 1, but very, very close to 1. And you can see the argument here. I'll just go through these very quickly. As we just saw earlier, the sigma, which is just proportional to delta, grows like t to the 2/3. And here's the value of sigma at some epoch, say recombination, could be any epoch. Then it scales like t, the epoch of recombination, divided by the horizon, by the Hubble time at that, by the Hubble time th. Now the horizon mass scales like th, and so putting these two together, you can see that sigma then scales like m to the minus 2/3, because the mass, the perturbation has the horizon. The mass of the perturbation is equal to the horizon mass, approximately when it comes inside the horizon. And so sigma then scales like m to the minus 2/3. That would be this alpha. So to get minus 2/3 here, you need n equals 1. And so, or alpha equals to 2/3. So that then is a very simple argument that shows that provided fluctuations have the same amplitude when they come inside the horizon, as we think is the case in inflation, then we end up with this very simple n equals 1 power spectrum. Now, in fact, if you do this properly, you find that n equals 1 is not exactly what inflation predicts. Inflation predicts that n should be slightly different from 1. And if we measure that n was exactly equal to 1 to infinite precision, then you could actually rule out inflation, because n should not be 1, but it should be very close to 1.
Why is that?
Let's come back. Let's do that in the discussion, because it'll take me a little while. Okay, so now then we right. So I talked about free streaming, and depending on the so the free streaming was this process through which fluctuations were damped away if they came inside the horizon when the particles were relativistic. And so it turned out, it was recognized in the early 1980s that from the point of view of cosmology, that was extremely convenient, because you could classify this still unknown dark matter particle into 3 broad families, depending on when this process of going from being relativistic to being non-relativistic happened. If it happened very early, then the particles would be cold, and we have a cold dark matter model. So these are particles that go non-relativistic very, very soon, or in the case of certain candidates, the axions, these particles are never relativistic because they're never in thermal equilibrium. So the axions are born outside of thermal equilibrium, and they're intrinsically cold. A supersymmetric particle with a mass of greater than 100 GeV would go non-relativistic very early on, and so the free streaming length would be tiny, and that's why these particles are cold. And then at the other extreme, they're hot particles, the best example of which would be a neutrino with a mass of a few electron volts. And I should have pointed out in the transparency I had early on, when I listed the contents of the universe, and I gave you the expression for the contribution to omega in the form of neutrinos, that if the neutrino had a mass of order 10 electron volts, it would contribute enough energy density to close the universe. So now neutrinos are very light particles. They stayed relativistic for a long time, and so they then experience this free streaming, which, as I said, the wavelength is inversely proportional to the mass. The mass is very small, and so this wavelength is quite large. Show you a picture in a minute. And then in between, there would be a warm particle, an example of which could be a sterile neutrino. Warm dark matter came out of fashion. It was introduced in the 80s. I think this nomenclature actually goes back to Dick Bond. But for a while, warm dark matter didn't really feature because there were no particle physics candidates for it, although recently there's been a lot of interest amongst particle physicists on the possibility that there could be a sterile neutrino that would act as warm dark matter. So we then so inflation then produced a power spectrum with k proportional to 1 with p proportional to k to the 1 power. And then all these processes, Mesaros effects, free streaming, genes, phenomena, all these alter this primordial power spectrum, so that if we look at the power spectrum of recombination, then it is no longer k equals k to the 1, but it's been modified by a transfer function. And so it has this form. And this transfer function then contains all the information about all this physics, which in turn encodes the nature of the dark matter. So if we could actually measure this transfer function, we would then learn a lot about the identity of dark matter. Now, one other very simple fact that can be derived from those equations is that because of the Mesaros effect that causes fluctuations in the dark matter, cold dark matter to stall during the radiation-dominated era, then it's very easy to see that that makes the power spectrum asymptotically go to n equals -3 in that notation I mentioned earlier. So the power spectrum of cold dark matter, as we'll see in a minute, at large wavelengths, the power spectrum is proportional to k to the first power because of the Harrison-Seldovich spectrum, and on small scales it asymptotes to n equals -3 thanks to this epoch of reduced growth. So there are fitting formulae that encapsulate all, well, they just describe what comes out of calculating all these processes for hot dark matter, cold dark matter. And you can actually, for the students in the audience, you can download a very, very important piece of code that has really had an enormous effect in the field called CMB Fast, written by Matthias Aldarriaga and Juro Seljak, which solves the Boltzmann equation that Chungpei Mai was talking about yesterday, and incorporates all this physics and allows you to compute in detail the transfer functions for any mixture you wish of cold dark matter, hot dark matter, and radiation. So here's then the summary of what I said so far. Then the story then began in inflation, 10 to the -35 seconds, after the Big Bang with quantum fluctuations that established a Harrison-Seldovich spectrum and Gaussian amplitudes. And then when the wavelength comes inside the horizon, then it can experience damping, which depends on the nature of the dark matter. And so at recombination, for example, here's a power spectrum with this important transfer function. And here's what the power spectra would look like in the case of cold dark matter and in the case of hot dark matter. So what's plotted here, unfortunately, I just contradicted myself. I told you that P of k, I was going to use P to describe k squared. Actually, I multiplied by k cubed. So sorry, so there should be a k cubed P of k. So delta k squared is just the amplitude, that is the density in k space. K cubed is the volume. So if you multiply by k cubed, you have the total power on scale k, right? So that's what's plotted here. So as the total power on wavelengths of different scale, k is 2 pi over lambda. And so these are large waves. These are small waves. In fact, for orientation, I listed here some well-known astronomical objects. So galaxies would roughly have this sort of scale, galaxy clusters and galaxy superclusters. So here you see then the case of cold dark matter. These are very large scales. These perturbations are only coming to the horizon very recently, so physics has not had a chance to do anything to them. So on these large scales, we recover the Harrison-Seldovich primordial spectrum. So on these very large scales, you can actually see inflation directly. And then here's the effect of the Mesaros damping, which causes the power spectrum to bend and to asymptote to a power law with exponent 3 here on small scales. And if you do the calculation properly, there's actually a logarithmic term that comes in here as well. Here's the case of hot dark matter, where this case corresponds to a neutrino with about 32 electron volts. And there you see this cutoff wavelength that occurs on a scale roughly comparable to a supercluster. And so what you have here then is completely different ways of making the large-scale structure of the universe. In the case of cold dark matter, there's power on all scales. And so you expect small fluctuations of soft galactic size to be the first ones to collapse. And then the structure to build up hierarchically as larger and larger structures collapse on it, because most of the power in the power spectrum here is on small scales. So small scales form first, and then larger scales form subsequently in a hierarchical fashion. Whereas in the case of hot dark matter, there's no power on scale smaller than, say, a supercluster for this neutrino mass. And so there, the sequence of cosmogony would be exactly the opposite. The first things that would collapse would be superclusters, and then clusters and galaxies would need to form after that by some form of fragmentation of these very large scales. So they have two opposing sequences of cosmogony, a bottom-up or a top-down. Of course, today we know that the right answer is this one, we think, but this is still an interesting process which could be, in fact, operating at some low level if the neutrino has a mass. I think these sort of masses are ruled out, but if a neutrino has a smaller mass, some of these effects will be present in the power spectrum. And I'll tell you later how we can learn about the neutrino mass from measuring the power spectrum of the galaxy distribution. Now then, of course, the dark matter could have an intermediate type of mass. For example, a sterile neutrino would have a cutoff in between those two. And this, I should say, is not ruled out. On the contrary, there's quite a lot of interest in trying to investigate whether we can find measurable differences between, in the galaxy distribution, for example, or in the galaxy luminosity function, between the predictions of cold and warm dark matter. So again, going to summarize again. I have this picture that I like to show. I think you'll all know what I'm going to say, but I'll say it anyway. So here we are sitting on Earth and looking back in time to the epoch of inflation. Quantum fluctuations then produce these small perturbations in the early universe. Here's the Big Bang, the plasma era. Here's recombination. And then when the universe recombines, these fluctuations have been affected by the process that I've been talking about. And then these fluctuations then leave an imprint in the microwave background radiation, which we see today in maps like this one. And as I mentioned, these oscillations that we see in the power spectrum of the microwave background radiation go back to these coherent oscillations of the photon baryon fluid for subgenes mass perturbations early on. So we know how to calculate this power spectrum almost analytically. You can't really, you have to run CMB fast because, because just mathematically it's cumbersome, but the physics are perfectly well understood. There's no, if you know what the universe is made of, then it's all linear physics, small perturbations, and I basically, whoops, in longer than I was hoping, but nevertheless a relatively short time, have described everything you need to know, pretty much, about what happens in this phase. So that's very well established, and that's why the microwave background is such a powerful diagnostic, because it probes well understood simple physics. Then the question now is, how do we go from those small perturbations that we see in the microwave background with amplitude, fractional amplitude of order 10 to the minus 5 to the distribution of galaxies in the universe today, where the perturbations, for example, represented in the center of the Milky Way exceed 1 million. Oh, good. Still got 10 minutes. I thought I was running more slowly than that. So how do we go from this, through these 10 or 11 orders of magnitude in amplitude in the growth of these fluctuations? Now, so if we're interested, as we are just now, only in the dark matter, we'll be interested in the galaxies later, but if we're interested in the dark matter, then the only interaction that one needs to bear in mind is gravity, because the dark matter interacts only gravitationally. Once we are interested in the galaxies that we can see, then of course the problem is more complex, because we need to take baryon physics into account. Now, so there is a simple model called the spherical Topcat model, and Simon alluded to it yesterday, that describes how a perturbation would grow all the way to collapse through this complicated nonlinear phase. But it applies only to spherical perturbations, and in the simplest case, spherical perturbations of uniform density, although one can generalize the mathematical treatment to spherical perturbations with an arbitrary density profile. But it's for spherical perturbations evolving in isolation. And that is a sort of standard against which we measure more complicated calculations. Now, I don't know if everybody's familiar with the spherical Topcat model. I toyed with the idea of showing you some equations that describe it, but Simon convinced me that that would be beneath you, so I decided not to. I'll just show you a picture instead. And so what's plotted here is the size versus time. And there are 4 curves shown in here. This one refers to the expansion of the universe as a whole. This happens to be an Einstein de Sitter universe, but it's a very old plot. You can see it's going yellow when we used to think that omega matter was 1. Doesn't matter. This just describes the expansion of the universe as a whole. And these are 3 perturbations of different mass. This is a large mass, a somewhat smaller mass, and an even smaller mass. So let's look at the evolution of these perturbations. So all the linear theory that I've been talking about so far refers to the evolution here, right? And as soon as the perturbation, as soon as this dimensionless density contrast becomes a fourth unity, in fact, much before it becomes a fourth unity, but when the linear theory breaks down. And so linear theory only describes what happens here. Now, so here we have a perturbation then that is expanding with the universe, but because it's growing, then it's becoming heavier and heavier, if you like. It accretes more mass until it becomes so massive that it stops expanding and then collapses. And this spherical Topcat model describes how this collapse happens and when it occurs. And for example, Simon mentioned yesterday that collapse occurs when the extrapolated linear theory over density is equal to 1.69. So at this point, if you extrapolated the growth using linear theory, then the density contrast would reach this magical value of 1.69, and at that point, the perturbation would collapse. Now, what happens when the perturbation collapses? Say if it's cold dark matter, then the perturbation then, because these particles don't interact except through gravity, the matter goes through and then oscillates, and eventually the object becomes what we call virialized. Namely, it reaches a sort of thermodynamic equilibrium state, and the spherical Topcat model tells us that it does so at a radius that's half the radius of maximum expansion. So when the object virializes, then its radius is just half of the radius of maximum expansion, and the object, just by symmetry, in fact collapses at a time which is twice the time it took it to get to maximum size. So that's what would happen, say, for a galactic halo if it was perfectly spherical. A galactic halo would have done these oscillations several times because galactic halos in cold dark matter form early, so they have a time to oscillate several times and to become virialized. This is now what you would expect in the case of, say, a galaxy cluster. A much bigger fluctuation came inside the horizon later, and it maybe has executed only 1 or 2 oscillations. And is just beginning to virialize. And that's why when we look at galaxy clusters, we often see lots of substructure because these objects have not had enough time to relax, as much time to relax as galactic halos. This would be a supercluster, which perhaps is just beginning to reach maximum expansion and has yet to recollapse. And so the power spectrum then measures the way how these different wavelengths, how they contribute to the irregularities in the universe today. So now that's the case for a spherical perturbation. Now in reality, an isolated spherical perturbation, in the real universe, perturbations are not spherical and they're not isolated. And so the problem then becomes one of calculating how this evolution should proceed in this more general case. And for that, there's no analytical solution. There are analytical aspects that you can calculate analytically, and I think Simon has already mentioned some, and we'll talk some more about those. But in general, if you want to follow the evolution of a whole spectrum of perturbations in the expanding universe, just under the action of gravity, you need to use simulations, and I'll tell you about simulations next. But the main point then is that the basic physics is just gravity, so it's a simple physical problem. It's just complicated from the point of view of computation. So there are 2 kinds of calculations one might want to do with simulations. When it's interested in dark matter, as I just said, you need only to follow gravity. Of course, the moment we want to talk about galaxies, then we have to go to a completely new level of complexity and also solve the hydrodynamic problem. So I'm going to tell you a little bit about how we solve the gravity problem in simulations. So just some general principles first. You might wonder why, if we're talking about the universe, fluctuations that may be very large, of size comparable to the horizon, whether we need to use general relativity to solve the problem. And the answer, fortunately, is not. Otherwise, this subject would have not advanced as much as it has done if you had to solve the general relativity problem. And the reason is partly a coincidence, namely that if you calculate in the right gauge, as Jim Bardeen did 25 years ago, 30 years ago, the growth rate of fluctuations in relativity, it turns out that these growth rates are exactly the same as you predict in Newtonian physics, the ones that I was talking about a few minutes ago. And so, in fact, it turns out that relativity is not necessary for the most part in calculating the evolution of perturbations, even large ones, just because the growth rates, the relativistic growth rates, are the same as the Newtonian growth rates. And so that simplifies the problem enormously. Then in reality, you can imagine the dark matter to be a fluid, a continuous fluid, and which is described by the Blasov equation. So in principle, you need to solve the Blasov equation to follow these perturbations. And in practice, the way that's done 99.9% of the time is by discretizing this fluid and representing it with particles, M-bodies, which are a Monte Carlo representation of the discretized continuum dark matter fluid. So the dark matter is described by the Blasov equation. And what we do is to represent this continuous fluid by a discrete set of particles, each of which must be regarded as a Monte Carlo realization of this collisionless fluid. Now that then leads to a system. So you represent the dark matter by a system of particles, each of which, to say, must be seen in a Monte Carlo sense. And then you need to solve the interaction equations for these n particles. And so you end up with 3n coupled nonlinear differential equations of second order. So that's what you need to solve. And 3n because they move in 3 dimensions. And that's the problem you need to solve. Now, it's difficult to solve because if you were trying to do this naively, where you say, well, OK, I just need to compute the force between every pair of particles. And you can see that the time to carry out such a calculation would scale as the square of the number of particles. And you will soon run out of your computer time allocation. And so the art of embodied simulations consists of finding strategies for reducing the time that it takes to carry out this computation. Now, I think I better stop here because this is going to take me more. How many minutes have I got? 1. All right. So what I'm going to start. So I'm going to stop here, and I meant to go a few slides further, but I didn't. But what I will start with next time is how you actually go about solving this embodied problem, and what strategies you can use in order to make it tractable and to be able to do interesting calculations in a finite amount of computing time. So what I've done today, then, just to summarize, is set the scene of that prepares the ground for what will come next. Namely, I've described how these small perturbations evolved in the early universe and how they prepared the universe at the epoch of recombination, 400,000 years after the Big Bang, for the structure that we see in surveys like Sloan and 2DF to grow. I'll start then next time with a little bit of the techniques, and then I will move on to what the simulations actually predict and how we go about testing them against observations of the real universe.